Okay. Well, welcome back, everyone. So our conference has a time ordering, and the next talk in that ordering will be given by Rafael Chaves about implications of causal structures.
Yeah, thanks. First, I would like to thank the organizers for this really nice conference. It has been a lot of fun. Can you hear me? Yeah. Okay. So the results I'm going to present here, they are mainly based on these two papers that have been done in collaboration with many people, in special David, that's also here. Okay, so as you may know, recently there has been some quite fruitful exchange of ideas between the fields of non-locality and foundations and the field of causal inference. In both these fields, the basic question that one is interested, and is also the question that we are going to be interested in this talk, is the following. We are given some collection of empirically observable variables. Which are the correlations between these variables that are compatible with some underlying causal structure? This sort of question appears basically in any field where causal inference may play an important role, like from medicine to economy. So just to cite one concrete example, there is this curious effect that has been observed in the study of social networks, that people that are friends of obese persons, they are more likely to gain weight also. And given this observation, would like to try to understand what could be the underlying causal mechanism, right? It could be that really, as a direct consequence of the friendship, this person here may acquire some unhealthy habits, let's say, that after some time may lead to obesity. But this is just one causal model. It could also be something actually there is some pre-existing unhealth factors that not only may cause obesity, may also be the reason for the beginning of the friendship. Let's say both of them like to eat cake. Well, okay, so distinguishing these two possible causal models, direct influence from common causes, it's sometimes possible, and it's just one example where this sort of question appears in the classical setting. Of course, the same question appears in quantum information problems. Perhaps the most famous example being Bell's theorem, that basically states that quantum mechanics is incompatible with some set of causal assumptions that seem very plausible, at least classically, and we would expect to hold between experiments that are performed by distant parties, Alice and Bob. Okay, so here's the outline of the talk. To begin with, to put these two seemingly very different topics of research under the same mathematical description, I will introduce this notion of causal structures. And then we are going to see that this very general question, are some correlations compatible with some underlying causal structure? It's in general equivalent to the characterization of non-convex sets. And this turns out to be very hard. And it's really computationally very demanding and out of reach, even for very simple causal structures. So because of this difficulty, what we propose here is an alternative approach that instead of relying on the probabilities of the events that we observe, to rely on the entropies of these probabilities. And it's a very simple idea, but really allows us to move from this non-convex problem to a convex problem that it's much more tractable. We start doing that for the classical case, and then of course, as we know from yesterday from session, we should put quantum in front of stuff. So we move to the quantum case, and as a nice application of this generalization to the quantum case, we are going to see that one can, for example, strengthen this so-called information causality principle that has been proposed some years ago to try to explain the degree of non-locality of quantum mechanics. Okay, so we have a bunch of variables, the causal relationships between these variables. They are encoded in a causal structure that can be represented by this very intuitive graphical notation of directed acyclic graphs, or a DAG for short. So it's a graph. It means that each node in this graph denote variables, and these variables, they can be connected by directed edges that carry the information about causation. So for example, this variable lambda1 points towards A, meaning that it has some direct influence over A. Okay, the important thing here is that the causal relationships between these variables, they are encoded in the conditional independencies that are implied by these graphs. So what we mean with that, for example, lambda1 and lambda2, they do not have edges that go from one to the other, nor there is a third node that connect both of them. So this means that these two variables, they should be statistically independent, what is represented by this constraint here, this quadratic constraint. Similarly, there are other constraints that follow from this causal structure, like for example, the fact that A and B, their correlations are mediated by this variable lambda1. So given this variable lambda1, their correlation should be screened off. It's again like a conditional independence constraint. Okay, so given this a crash course on this what a causal structure is, like we can come back to the original question and ask how we can use these conditional independences to solve the following question. We are giving a probability distribution. Is this probability distribution compatible with some underlying causal structure? And of course, that's only the case if this probability distribution fulfills all these causal constraints that are implied by the DAG, by the causal structure, and these causal constraints are encoded in these conditional independencies. So just to see an example, let's say we have this probability distribution over 6 variables. Is it compatible with something like this? Well, that's only the case if it fulfills all the conditional independence that follow from this graph. These are only 2 of them, there are many. And for example, if one of them it's not fulfilled, well, then we know this is not a good causal explanation. So what we see here is that in general, if we have access to the full probability distribution of all the nodes that compose a given DAG that we are trying to understand, then this conditional independence, they hold all the information that we need to solve this problem. But of course, life's not that easy, and we are interested in usually in marginal scenarios. So what we mean with that is that for many different reasons, not all the variables in a given DAG, they are observable. Meaning that not all these conditional independence, that again, they hold the causal information, they are available from empirical data. So like as a typical example, well, it's just the causal structure that follows from Bell's theorem. We have Alice and Bob. They are distant and they receive particles like from, let's say, hidden source lambda. Hidden in the sense that we don't have direct access to what the source could be. Maybe there are some degrees of freedom that we cannot observe or something like that. And now, well, Alice and Bob, they receive these particles, they measure, they flip some coins, X and Y, and decide what to measure, obtaining outcomes A and B. And now, this causal structure implies some causal constraints, as we all know. For example, like this so-called free will assumption implies that X and Y, they are mutually independent and also independent of the hidden variable lambda. This is encoded here in the fact that this probability should factorize. This is a polynomial constraint here. Similarly, because of the locality assumption, it follows that there should be no arrow going from A to B and vice versa. What basically implies this constraint, implies this constraint that the statistics of what is observed by Alice, this A here, should not depend on whatever Bob is doing on his side. Similarly, there are other constraints that follow here, but the important thing that it's already on these 2 expressions is that this conditional independence that depend on this variable lambda, that's not directly observable. So this means that we don't have empirical access to this to check for these causal constraints. But as originally realized by Bell, I guess, these constraints on the level of the things that we cannot observe, they also imply constraints on the level of the things that we do observe. For example, this probability here, it's an observable one, probability of the outcomes A and B given X and Y. Just plugging in these causal constraints and making some trivial steps here, we see that any observable probability that it's compatible with this DAG, with this causal structure, should be decomposable in this way. This is just like a convex sum, so it implies that the compatibility region associated with this graph here, with this causal structure, it's a polytope that we know can be characterized in terms of finitely many inequalities, that in this context are just the famous Bell inequalities. Okay, so you see what's going on here. Like we are given a causal structure, we want to characterize its compatibility region, like for example this local polytope, this local hidden variable polytope, and we are giving a point, a probability distribution, and we want to see if this point falls inside this or outside. Then we can check for compatibility. Okay, so that's the challenge, like to describe marginal information that it's compatible with some underlying causal structure. Of course, that the full causal information that it's empirically available, it's contained in the probabilities of the events that we observe. But analyzing these probabilities turn out to be very difficult because in general we are going to deal with non-convex sets. So in the case of Bell, of course, like we know it's this nice polytope that in principle we can characterize using like a linear programming, but in general that's not the case. So just to see one example, like we have this causal structure again. Sorry. where now we have A, B, and C that are the observable variables. But the correlations between these observable variables, they are mediated by these hidden variables here that are mutually independent. And this mutual independence, like the fact that they have no arrows here going around, implies that on the level of the things we can observe, anything that it's compatible with this causal structure should be decomposable in this highly nonlinear way here. That basically implies compatibility regions of this form that may look very beautiful but can be terribly complicated to be characterized. And you see the point here, well, okay, just to mention that in principle one can characterize these things like using things that come under the name of algebraic geometry and quantifier elimination methods, but the point is that these, like they have general algorithms to describe these things, but they are really computationally super difficult, like really demanding. And even like for very simple causal structures like this one, these methods, they just are out of reach. But you see, the problem is arising here because we are trying to use the full causal information as it's contained in these probabilities of these events that we can observe. But if we relax this assumption that we need to use this full causal information, I have 15 minutes or, yeah, okay, thanks. Maybe the problem may simplify, and that's the main idea behind our approach here, that instead of relying on this full causal information as contained in the probabilities, to rely on the entropies of them. And the main reason for doing that is that we simplify the problem. We turn this non-convex problem, in general non-convex problem, into a convex problem, while still really retaining a lot of useful causal information. So let's see how this works. First for the classical case. Okay, so the approach here, it's really simple. It consists of three steps, and in the first step, so we are given a DAG, a causal structure that it's composed by n variables. In this first step, what we want is to describe the constraints that the constraints on the entropies that follow for any collection of n variables, like regardless of any underlying causal structure. So to do that, like we construct these entropy vectors, like these vectors in this real space, are to the n, where n is the number of variables in the DAG. But now you notice that not every vector is an entropy vector, because vectors, they should respect some constraints. For example, they are positive. The region of the real space that characterizes these entropy vectors, it's known to be a convex cone, so it's an object like this that can be characterized either in terms of the extremal rays or the facets. It's kind of similar to a polytope. It's just like a unbounded object. The point is that the structure of this animal here is not known. Like it's such a basic object, but we still lack a really good understanding of what this thing is. But the point, and what's important for us here, is that what is known is an outer approximation to this convex cone. That's those so-called Shannon cone. That is very nice because it's characterized by basically two types of very simple inequalities: strong subjectivity and monotonicity. These two sort of inequalities here. Okay, so this is the step one. Just list out these constraints that characterize the Shannon cone. Now, the second step, we choose the candidate structure, and we add these causal constraints. Okay, remember these are the conditional independence that follow from this graph, and in terms of probabilities, there are these nasty polynomial constraints that are very difficult to deal with. In terms of entropies, they are very simple. They are just linear relations, basically saying that some mutual informations should be equal to 0, or some conditional mutual information should be equal to 0. And what's more, we can even relax that. We can relax the causal constraints in a very easy way. For example, saying that they don't hold exactly. Like we may have from empirical data, may only have confidence like about some epsilons, let's say. Okay, so you see like what the object that we are interested here, it's still a convex object. It's the intersection of this unconstrained cone with the linear, with these linear inequalities that encode the causal assumptions. This is step 2. Step 3, what we need to do is to marginalize. So what we mean is it's something like that. We don't have access to all the variables in a given DAG, so we need to eliminate the entropies that correspond to these variables from our description. It's the same thing as in Bell's theorem. But remember that what we are given here, it's an inequality description of these convex objects. So basically, we have a set of inequalities that describe them, and we need to eliminate from the set of inequalities terms that correspond to entropies that we cannot observe. Well, one can do that, like for example, resort into these Fourier-Motzkin elimination methods. But the final result here, after these 3 steps, is the following. We have a linear description, like in terms of linear inequalities, of the entropies that are compatible with some underlying causal structure. Thanks. Okay, so there are many applications of this method in the classical case. To move to the more interesting quantum case, let me just mention some of them. For example, like one can understand this framework as a way to basically like derive entropic Bell inequalities for any Bell scenario, like a kind of generalizing the results of Bronstein caves that are already quite old. Okay, let me choose another one. This one here, like I'm actually like quite excited about this thing because now, so one can quantify causal influences. What we mean with that is that not only we want to assign a causal structure to a given observation that we have, we also want to quantify that. So like given some observations, what is the minimum direct causal influence, let's say, between these 2 variables that it's required to explain what we observe. And using these ideas, we can do that like quite generally. It's very interesting. Okay, so now let's move to the quantum case. Well, the idea, it's going to be basically the same, like we're going to have these 3 steps, but now we need to pay attention to a few very important differences. But the first thing to notice is that there is not a unique definition of what a quantum causal structure is. Yeah, this is just a highly incomplete list. But for us here, what's important is the following, is that just to have a graphical representation that easily, or as easily as possible, allows us to generalize this entropic approach to the quantum case. So for us, like these quantum causal structures are nothing more than like something, well, in this case, a graphical notation that specifies the functional dependence between a collection of quantum states and some classical variables. So let's see how this works. Well, the graphical notation is going to be very similar. Let me just introduce some of the building blocks here. We again are going to have edges and nodes, but now the nodes are of 2 types. We have classical variables that are denoted by these round edges here, and we have things that denote quantum nodes that well, are these square edges that are labeled by the systems that they represent, and they stand for like the density operator of these quantum systems that they represent. And we also have like these sort of things like that represent quantum operations or completely positive trace preserving maps. So now we have incoming edges that are associated with these nodes, where both carry the labels of the systems that they represent. And of course, like this is just saying that this is a quantum operation from this system here to this system here, like something like this. So just like a simple example of a fully quantum causal structure, like node C here, it's obtained by applying this quantum operation, denoted by this phi here, on a state that factorizes. And the reason why it factorizes, you see here, because they do not have arrows from one to the other, nor there is a third node that connect them, so they should be independent. Okay, so like with these building blocks, one can basically construct any causal structure that you like and try to analyze what are the entropic corollaries of these quantum causal structures. So like first we need to adapt our method for the classical case, for the quantum case, like to give this entropic description of quantum causal structures. And it's very useful to just use this example again. It's very similar to what we had before. These are the variables that we can observe, A, B, and C. They are classical variables. But now their correlations are mediated via some hidden, let's say, quantum states. Like you see now that they carry these edges, they carry these labels. Okay, so the first difference is, of course, that we need to replace the Shannon entropy that we had in the classical case with the von Neumann entropy. Remembering for the case where we are looking for things like entropy of A or entropy of AB, they should coincide. So it's okay to use the Shannon entropy again. Perhaps the first important difference is this one here, that now remember that in the first step of this approach, what we do is to list all the inequalities that follow for any collections of n variables. And these were a strong subjectivity that also hold for the von Neumann entropy. And we also used monotonicity, that because of entanglement, it's not going to hold anymore. So like whenever this is the case, we just replace monotonicity by the weak version of it. The next point, well, okay, it's perhaps the most important one, is the fact that measurements for, like, in general, quantum operations, completely positive and trace-preserving maps, they destroy the quantum system that they act on. So what we mean with that is the following. So let's look at this variable A here. It's a classical variable. For this classical variable to assume a definite value, to assume an outcome, what we need to do is to apply some joint operation on its quantum parents here, on its on these two quantum states. But by doing that, we disturb these states, right? So what I'm trying to say is that A1 and A2, they do not jointly coexist, with their classical descendants. So this means that we cannot assign entropy to this sort of objects. And this has a very serious consequence to our approach, right? Because remember now, the causal constraints, they are encoded in these conditional independencies. But if these objects, they don't exist anymore, we cannot define them, this means that we cannot define these conditional independencies. For example, the fact that A and B, their correlations are mediated via this common ancestor here, but now this term involves, for example, the entropy of A with A1 that do not jointly coexist, so we don't know how to assign an entropy to this object. Just as a side remark, like conditional independencies, they in general will not hold, but independencies they still hold. For example, the fact that these quantum states, they're produced independently, so they should be independent. Like their meet information should be 0. Okay, and now because we don't have these anymore, like we don't know how to encode this conditional independence, we need a rule that kinds of replace that. And we achieve this by using data processing. That basically, well, it's also it's valid for quantum too, and basically states that locally manipulating like a quantum system, you cannot increase its information content. Okay, so like basically now we can follow this 3 steps approach that we had for the classical case, like just paying attention to these very important things here. Okay, so let's see this in practice. There are like some applications that we know about of this framework, but let me just cite one. The information causality principle. So as you know, like quantum mechanics is not as non-local as it could be, like while still respecting, for example, non-signaling. So like because of that, people try to come up with like other principles that could try to somehow single out quantum mechanics or try to explain why it's so special. One of these, it's information causality that can be understood as usual as a game between Alice and Bob. And the point here is that this game can be faithfully represented as a quantum causal structure, where the only quantum node here, it's this one. So the game goes as follows. Like Alice receives some input bits, x1 to xn. Bob receives some input, some random variable s that tells him which bit x of s he should try to guess of Alice. And the resources that they have to perform this task are the following, like some pre-shared correlations, for example, arising from measurements on an entangled state, and a classical message that it's sent from Alice to Bob. The point here, and like information causality, the original inequality makes this intuition precise, is that the amount of information that Bob should have about the inputs of Alice should somehow be upper bounded by the amount of information that it's contained in this message M, right? Like in the case where you have no message, he should have no information whatsoever. And well, we have this inequality here, and now, but the point is this: like we have this quantum causal structure, and we know how to derive entropic constraints for it. But remember, the first thing we need to do is to define a marginal scenario. And in this, in the original paper, they kind of implicitly use this marginal scenario here, where you have like the entropy of M and the entropy of these collections of variables here, like the guess I and the bit I, xi of Alice. And if we proceed with this marginal scenario, with this general framework, what we see is that this information causality inequality is the only non-trivial facet of this entropic causal cone. So it's basically like giving this geometric interpretation to what this means. Thanks. But now you see that this is not the most general marginal scenario. The most general one would be something like this, where now, for example, the guess 1 of the bit x1 of Alice may also contain information about the other bits. So this is the most like, this is the scenario with that has all the available empirical information. And if we proceed now with this marginal scenario, what we see, it's very interesting that these, like we have a bunch of new kinds of inequalities, and in particular, one of the facets of this entropic cone is a tighter version of the information causality inequality. So what this is saying is that the proper analysis of this quantum causal structure reveals that the original principle is not as tight as it could be. And of course, because of that, there are points that are post-quantum that could not be detected by the original inequality, but can be detected by this new one. And just as a side remark before I finish, one can easily generalize this to the case where now the message is quantum, like in a kind of dense coding protocol. And the basic difference is that now we are going to have a 2H of M here. Like, as we know, like sending quantum systems, we can somehow double the amount of information. Okay, so just to finish, the main idea here is that this entropic approach provides, let's say, nice, feasible, but still like a very useful tool to analyze these causal structures with applications in both the classical and quantum problems. And there are a few things that we would like to know, like applications of these in like let's say relevant problems, like medicine problems, like reconstruction of genetic networks. And from the quantum case, we think that there are many things. Like, for example, use this approach to generate Bell inequalities for both the classical and quantum cases, like in the case where we have like these networks, not only one source. And similarly, well, there are some other things one can think of. And well, with that, I'd like to thank you.
So we have time for a few quick questions before the next talk.
This point that you can witness the non-quantumness with the new information causality inequality, where does it lie in the NPA hierarchy? In which Q1, Q2, Q3?
Well, okay, we don't know. Like, let me just show you a graph here. So this is the original information causality inequality, this orange one here, and the new one, it's here, this red one. So you see that the gap, it's quite large, but we haven't analyzed that. But I believe one can go quite down in this hierarchy. It's what we hope, but we haven't analyzed that yet.
Thanks.
I mean, even information causality, we don't know how to compare to NPA, right?
Yes, like there were this conjecture that it turns out to be wrong. I think that information causality should be in the first level of the hierarchy, but like I think someone found a counterexample, so it's not known. Yeah.
Okay, if there are no more questions, let's thank Rafael again.